Hello, I'm Professor Congleton, and this is Econ 421, Introduction to Math Econ. This is a pre-recorded lecture that will be filling in for me while I'm away at Japan. And this is the first of the two lectures that I've recorded for this class. So what we're going to do today is to talk about comparative statics. We have in the past done some comparative statics in a kind of informal way by creating a model, finding out the implications of the model, in particular the equilibrium implications of the model, solving for the equilibrium, either a market equilibrium or an equilibrium in some contest or another. And then we've pointed to those conditions that describe the equilibrium and kind of discussed how parameters of the choice problem might change and thereby affect the equilibrium. And what we're going to do today is just kind of basically review that methodology and be just a little bit more precise and general than we have been in the past. Because we've done really a wide range of models so far in the course, what I'm going to do today is go back to some of the early models that we worked on in the first part of the semester and use those as kind of a basis for thinking about changes in demand, for example, that might affect prices or market sales. Okay, so what I'm going to do is, as usual, is kind of fill the little whiteboard here with some math. I'm going to try to keep it short. And again, remember, if you're watching a pre-recorded lecture seriously and you're taking notes, there's a pause button you can hit. And so while you jot something down, and that will allow me to just kind of proceed through without being able to see you guys and tell whether or not you're actually writing or thinking or how you're interacting with the lecture. Okay, so because I can't see you all, this is a second best solution to the problem of delivering a lecture, but it's far better than nothing. And I hope you'll find it useful in preparing for your last quiz and also for thinking about the papers you'll be writing in the next couple of weeks. So what I'm going to do is talk about utility first. So we're going to have standard utility function, and I'll use one of our standard forms. All right, so we're going to do our standard multiplicative exponential form, of which the Cobb-Douglas function is a special case of this, where the exponents add up to 1. But generally speaking, I prefer exponents that add up to less than 1, or to some other number than 1, because 1 often causes trouble when you do comparative statics and things of that sort. Doesn't always, but it can. And we're going to have a budget constraint. Which is basically, again, just wealth is equal to the price of good one times quantity of good one, and the amount, and that gives me the amount that I'm spending on good one, plus P2 times X1, price of good 2 times the quantity of X2 that I buy, which is the amount that I spend on good 2. You add those two things up, we should get W. So if we form a Lagrange from this, we'll know that this will be something like X1A, X2B, minus lambda W minus P1 X1 minus P2 X2. We'll get 3 partial derivatives. All right, and we can use those partial derivatives to determine the demand for each of these goods. I'm going to focus on good 1 just because I'm used to doing that, and it's kind of pretty easy to do. So what we're going to do is kind of shift these lambda terms over to the right, and we'll then do a division of the two sides. Since they're both equal, that can be done. So this term here can be thought of as the tangency condition between an indifference curve and a budget line. Okay, this would be the slope of the budget line, at least it would be after we cancel out the lambdas. And this would be the marginal rate of substitution, which is the slope of the indifference curve at the point of tangency in this case. So if we do the arithmetic here, we'll get right, in effect, we take this term divided into this term, get x1. We take this term divided into that term and get x2. Then we solve for x1, which will give us right, so we multiply the x2 across and divide this term back across, and we get a over b times p2 over p1 times x2, and that'll be x1. Okay, so this term describes the relationship between x1 and x2 along possible budget lines that you might confront. We have a specific, or rather a kind of a general form budget line that we're going to deal with here, which is determined by this budget constraint. So we can substitute that into this term into the budget line to get right, so as it turned out, I'm solving for x2 instead of x1, so I surprised myself. And what we're going to try to do is factor this out and then kind of shuffle terms over this way. So over on this side, we've got everything has an x2 involved with it. So we want to factor that x2 out and see what we get. Okay, so maybe before we get going too far, we'll cross these two terms out. If we put P2 over a denominator, that will be, or B, this will be A plus B over B times P2 times X2. Oops. Okay, so the demand for for good 2, which is what we just solved for, is a fraction of wealth that's constant, which is standard for this type of utility function. And the fraction is basically the exponent of the good we were interested in, which is the exponent for x2 in the utility function, divided by the sum of the exponents. Remember that in a Cobb-Douglas formation, a plus b would be 1, and this would just be b times wealth, divided by the price of the good that we're interested in. So in these exponential functions, the whole family of them, okay, the demand curve basically depends only on the good's own price. It doesn't depend on the prices of other goods. And that's an unusual feature of this particular family of functions. It won't be true for all functions, but it does make the math a bit easier. So if I know the fraction of wealth I have devoted to this good 2, then the amount that I buy just moves along with price. I just divide price into that amount of money, and that tells me how many units of the good that I'm buying. Okay, so let me recopy that and maybe make it a little bit neater. So if this is the average consumer, for goods 1 and 2, and there are end consumers, then the market demand for X1 is just N times A over B plus A times W over P1. Oops, moved on that one. And for X2, it is just N times B over A plus B W over P2. All right, so that derivation just took a few minutes, after all the hours of practice that we've had during the semester kind of working with these functions. So notice that we can think about the effect of changes in the consumer's choice problem and how they affect the demand curve, where that demand function is located. So for specific values of N, A, and B, and W, and P1, we would know exactly how much the person was buying. Okay, for a demand curve, we usually leave P1 abstract. And if we want a specific demand curve, we would have a specific N, a specific A, a specific B, and a specific W. Right? That would determine a particular demand function and a particular demand curve. And that would be true over here too. We'd have to know the number of consumers, the exponents that go with the demand curve, B and A, and we'd have to know the amount of wealth that the average consumer has at his disposal or is planning to devote to these two goods, which would be W. And we don't need to know the other price, because the other price the demand curve tells us kind of what's going on with with prices. Okay, so if we just look at comparative statics, of demand, these are generated by changes in tastes, which are A and B, income or wealth, W, and the price of the good. The price of the good and the number of consumers. Right, so we've got 1, 2, 3, 4 variables, which for the purposes of deriving a demand curve, we normally hold constant. We just assume that they're fixed for the period of identifying the consumer's demand and the market demand. But when we're doing comparative statics, once we find out what the demand curve is, you want to think about how those variables, how changes in those variables would affect the level of demand. And so that means basically we want to take derivatives of the quantity demanded, x1 star or x2 star, with respect to these other variables. And that will tell us something about the direction the demand curve moves. Does it shift out? Is the derivative positive? Or does it shift back? Is the derivative negative? So we use we use derivatives in this case not to find a choice, but to see how changes in a parameter affect choices. For example, so if we take the derivative of this function here with respect to W, we're going to get n times A over B plus A times 1 over P1 is greater than 1. So demand shifts out as W increases. All right, so if that partial derivative is positive, then we know the whole demand function just moves out when that variable is increased. Okay, normally when you look at the derivative, when you're doing comparative statics, what you're doing is identifying the effect of a very small change in whatever variable you're looking at, right? An infinitesimal change in principle. But the same thing will hold up for kind of larger changes, right? Because if you get a single result that is always positive, then you know it's positive the first little one, the second, third, fourth, fifth. And so the cumulative effect of significant changes in wealth is simply a greater increase in the shift of the demand curve out to the right. Right, so if this is the demand curve, this is Q and this is P. We're getting an increase in quantity generated for every point on the demand curve generated by a change in wealth. And we can also see dx star dn. Again, using it this function again, it's going to be a over b plus a times w over p1, which is also greater than 0. So the same, pardon me, I should have been a 0 there, pardon me. So again, that change will also cause the demand curve to shift out. Now, changes in taste are a little bit trickier to figure out because they're in this fraction, so the derivative is a little more complicated. It's not always just a simple, clean result. It includes two terms. But for example, let's do dx1 dA. Okay, so as far as that derivative is concerned, it's just like n times w over p1 times the derivative of this term, and that would be 1 over b plus a plus, or pardon me, minus a plus b squared. Okay, so when you look at that, it's not quite as obvious that the whether this is positive or negative. And so what is sometimes useful is to kind of figure out what's going on here. Which of these terms is bigger? So if I put this over a common denominator, I'll have to square this term. And that will give me a b plus a in the numerator. And you can see that that will just subtract out. That a will just subtract out. And that eliminates the second term. And therefore we can tell that this is also greater than 0. So this is another change that would tend to shift the entire demand curve out. That is to say, the quantity demanded at every price increases as any of these three changes occurs in the choice setting or choice environment of the consumer. More consumers, stronger taste favoring the good of interest, more wealth. All those things tend to drive the shifted whole demand curve out. Now notice that when we write down a demand curve, we actually are capturing the relationship between price and quantity, holding all those other variables constant. And comparative statics, in a sense, we're dropping that assumption. Okay, but we don't drop it until we've got the demand curve as a rule. And so we want to find out what the demand schedule looks like, because that's thought to be a fundamental relationship that's really important to economics. And if you don't understand that relationship, you can't understand market prices. But on the other hand, if you want to think about how prices change through time, you have to think about how demand curves and or supply curves change through time. And in order to understand those changes, you have to think about how parameters of the original choice problems for the firm and for the consumer affect the location of the demand and supply curve. And that's what we're doing with these comparative statics exercises. We could also have done a derivative with respect to B, which would look kind of like this one, but it would be the opposite, right? In that case, the demand for X1 would be reduced, even though the original exponent isn't changed. The fact that the other good becomes relatively more important implies that more of the money that is being allocated between these two goods will be devoted to good 2, for the good with B as its exponent in the utility function. Now, in order to know what's going on with prices, we need to have a supply curve of some kind, right? And so any change that shifts the demand curve out to the right, remember it's a q direction in which the change is taking. So people often say the demand curve shifts up, but it really shifts outward in response to all the changes we've been looking at. And you can see that for an upward sloping supply curve, all three of these effects on demand tend to have the same effect on price in terms of its direction of change, right? Direction of change is up. The price will be rising as a consequence of this outward shift in demand, other things being equal. And the quantity sold will go up, even though the price is rising at the same time. So this way of thinking about comparative statics is similar to what you do in a principles class or in an intermediate micro class. However, we now know why it is, and we can that when the number of consumers increases or the average wealth of consumers increases, that demand curve shifts out. Okay, we can track that effect through the mathematics instead of our intuition or the stories told to us by our professor. So there are exceptions to this rule, but for many of the ordinary families of functions that we take that we use to derive our demand and supply curves from, it turns out that these types of relationships hold up. Okay, well, we can't know that for sure by looking at a single family of functions, even though this family is quite broad, includes all kinds of possible values for A and B. Still, they're in a relatively narrow family of functions. So what we might want to be able to do at some point is to say, well, can we generalize this further? Can we go beyond this family of functions, even though this family actually includes an infinite number of members? Can we get an even larger set of functions and show that there's also general relationships that hold up in those cases? Because if we can do that, then in terms of understanding qualitatively what's going on with supply and demand, what's going on with market prices and sales, we can qualitatively, that is to say, we would know whether prices are rising or outputs are increasing or vice versa after we've done, without having to do too much work in practice. And that type of mathematics that we're going to look at next, actually in a couple of lectures, is behind the intuitions of your college professors when they tell you, why that a particular demand curve shifts out or a particular supply curve shifts up, or the prices are going to rise on average. They have that mathematics in the back of their head when they make those claims. Okay, whereas what you have is basically the word of your professor and your own kind of natural intuition as an amateur economist. So I think we could do more with this. In the lecture notes, go through an example where I derive a supply curve as well and show how you can integrate the two and look at use comparative statics to talk about changes in equilibrium prices. But I think for this recorded lecture, it's enough to show you that how it works for a family of demand curves that we've looked at before. And you can also see that if you went back and looked at, say, the lottery representation of a contest, that there are certain parameters of those contests that also are being taken as given for much of the exercise in order to determine the Nash equilibria. But once we found the Nash equilibria, we can often change some of those settings, like the size of the prize or the number of players, and that will tell us something about how much extra effort the participants in the contest will devote to it. And also the probability that one side wins or another side wins, right? Which in these symmetric contests would always be the same, but the probability of winning would tend to fall, of course, as the number of entries increased. So with that, I think I'll stop for today's short lecture and turn you back to the notes, which do a good job of going through a couple of other illustrations. And the next lecture I'll record will be an introduction to more abstract functions, which we'll use after I get back from Japan to talk a little bit about comparative statics in very generalized families of functions. And so that's all for today. Thank you.